A very good morning to all of you. I am Mr. Rich. Thank you for joining me. Very recently, I presented a comprehensive introduction to hyperbolic sine and hyperbolic cosine. In this one, we are introducing the other four functions, which you will all imagine in your head to be the hyperbolic tangent, hyperbolic cotangent, the hyperbolic secant, and the hyperbolic cosecant. For any of you who plan to do perhaps AP Math, Advanced Math exam, or even going to calculus, having the basic functional understanding of these hyperbolics is imperative. Even though we're not doing anything with regards to limits or derivatives or integrals, just having the base understanding of these hyperbolics puts you a step ahead of everyone else. So let us begin everything with this video here. You know, for hyperbolic sine and hyperbolic cosine, I presented the definitions for you in the previous video, and from these definitions the other four hyperbolic functions will come about. If you remember this to be e to the x minus e to the minus x over 2, you remember hyperbolic cosine to be e to the x plus e to the minus x over 2. When you're thinking about now this, the hyperbolic tan hx is we can call it that. You can think of it as hyperbolic sine divided by the hyperbolic cosine. In terms of the definition of this, you can just take this and divide it by this. You'll have e to the x minus e to the minus x over 2 divided by e to the x plus e to the minus x over 2. These 2's cancel out. You end up with e to the x minus e to the minus x or e to the x plus e to the minus x. That right there is a definition which you should know for the hyperbolic tangent. And it's very interesting to know that. Also, if you ever want to be going into calculus or taking the advanced math exam, the standardized AP math calculus exam, this is something you need to know. Everything I'm presenting you here in this video, you'll need to know for the AP calculus exam, which a student would take in high school, American high school, and go into American college, or anyone from abroad thinking about going into American college and wanting to take credit for this advanced placement exam, then everything in this video is relevant. The graph of hyperbolic tangent is something like this. You have a asymptote over here. The asymptote over here is y is equal to 1 and y is equal to minus 1. Right here, y equals 1, y equals minus 1. The graph of this, and I've shown you the graphs of these two in the previous video, hyperbolic sine and cosine. Just know this, it would look something like this, very much like a arctangent graph. Inverse tan, the hyperbolic tan is like that, except in the arctan, the inverse tan, you had asymptotes of y equals pi over 2 and minus pi over 2. Here the asymptotes are y equals 1 and y equals minus 1, and this is it. This is what the graph of hyperbolic tan looks like. The domain, as you can imagine, is minus infinity up to infinity. The range, as you can imagine, is stuck right here between these two asymptotes, but it won't include the values of those asymptotes. Asymptotes is minus 1 to 1, not including either, but everything in between, and there it is. The hyperbolic tangent. The hyperbolic cotangent, cothx, is now the hyperbolic cosine divided by the hyperbolic sine. You can imagine everything here would be exactly this definition divided by the other definition, with the 2's cancelling out. You'll have e to the x plus e to the minus x divided by e to the x minus e to the minus x. The divided by 2's in both instances cancelled out, and this right here is the definition of the hyperbolic cotangent, and there it is. You got to keep this in mind. Now in terms of the graph, it's very well adapted from the hyperbolic tan. You have the y equals 1 and y equals minus 1, except now you have a vertical asymptote right here. Your y-axis, your function would look something like this. There it is, stuck right here above and below these horizontal asymptotes and around the vertical asymptote, and there it is. That's your graph. And the reason why it is, you can zero out the denominator. You can zero out because if you were to put 0 in places of x, you'll have e to the power 0 minus e to the power 0. You'll have 1 minus 1. You'll have something here, a value here on the numerator, which is this, divided by 0. You'll zero out and you'll undefine, and you'll create a vertical asymptote, which you cannot do so for the hyperbolic tangent. And you can verify that for yourself, because in the hyperbolic tangent, this here serves as your denominator. If you put zeros in places of x, you cannot zero it out. You cannot make that function undefined, but this function can be made undefined with an x-axis of value of 0. You have an undefined in terms of your output, a vertical asymptote here of your y-axis. So keep that in mind. Anyhow, when you're looking here at the graph of this hyperbolic cotangent, now you can see the domain and the range are not too difficult. The domain is the left to right. You're looking here from minus infinity up to 0. Then you jump across, then 0 up to infinity. There, as you can see it. the range here, as you can imagine, you're coming here up to the asymptote. From minus infinity, you're coming up to -1, but not including -1. Then you jump across onto the other asymptote, and from 1 you go on towards infinity, and there it is. The domain and the range for the hyperbolic cotangent, keep this in mind, is very relevant. The last two, the hyperbolic secant, the hyperbolic cosecant, are easy. Let's look at the hyperbolic secant. It would look like this: SECHX, the hyperbolic secant. You're just taking the hyperbolic cosine and you're doing its reciprocal, because cosine and secant are reciprocal of one another's. Whether it's trigonometric or hyperbolic, the reciprocal relationship retains. You're looking at 1 over e to the x plus e to the minus x over 2. When you flip everything around, you're looking here 2 over e to the x plus e to the minus x. Again, you cannot zero out the denominator in any way, but you can develop a good y-intercept. And that y-intercept, if you were to put x-axis value of a 0, you plug it in, you're looking here at a 2 over e to the 0 plus e to the 0. You're looking at a 2 over 2, which is a 1. So you have a good standard point on your hyperbolic secant, which is your y-intercept 0, 1. And your graph looks something like this, right over there. You remember the hyperbolic cosine looks something like this, right? Like kind of a bit of a parabola. You're just making it in a reciprocal relationship, and that's what it looks like. And now you can imagine in terms of a domain, you're seeing over here there's a horizontal asymptote, your x-axis, but there's no vertical asymptote. Anyhow, the domain here is a minus infinity up to infinity, and the range you can see is what? You're going from right here up to right here. It's going to be 0 up to 1, but 1 value is included because this right here goes through 0, 1. You see 0 is not included because it's a horizontal asymptote, and y equals 0 is a horizontal asymptote, but 1 is included because it falls on the curve. If you put 0 in this function hyperbolic secant, you'll get an output of a 1, 0, 1. And that is the relevant information you need to know about this. Our last function, is the hyperbolic cosecant, the reciprocal of hyperbolic sine. And you can see it'll be 1 over e to the x minus e to the minus x over 2, and you'll get 2 over e to the x minus e to the minus x. Now, this will have a horizontal asymptote, your x-axis, and it will have a vertical asymptote, your y-axis. If you put here in terms of x a value of a 0, you'll have e to the 0 minus e to the 0. You still have this 2 on the top. You'll have 2 over 0, and you'll have it undefined. So you have a vertical asymptote here, your y-axis, because the function becomes undefined if x-axis values are 0. Keep in mind, when you do this, when you do sine h of a 0, you get a 0, but when you do cosine h of a 0, you're getting a 1. And you can do that very easily on your calculator and verify it. Remembering this specific aspect where helps you also think to the vertical asymptote development. If you do 0, you're doing hyperbolic sine, you're getting a 0. But if you're doing 0 hyperbolic cosine, you're getting a 1. Which is why when you're looking at the hyperbolic cosine's reciprocal, the hyperbolic secant, you're not seeing a vertical asymptote. But when you're doing the reciprocal of this, which is this, you're seeing a vertical asymptote. Likewise, again, for the hyperbolic tan and hyperbolic cotan, in the hyperbolic tan, the cosine is in the denominator, you can't zero out. In the hyperbolic cotangent, now the hyperbolic sine is the denominator, and you can zero out the denominator and you get the vertical asymptote. This hyperbolic cosecant, as I've told you, has a horizontal asymptote, your x-axis, and a vertical asymptote, your y-axis, and the graph looks like this. Right over here. It looks very much like a reciprocal function. Remember this to be the graph of hyperbolic sine. Well, you're just doing the reciprocal of everything here in this quadrant and reciprocal of everything in this quadrant, and this is what you get. That's exactly what you get. And we can develop the domain and the range. The domain is going to be, again, minus infinity coming up to 0. Then you jump across your y-axis, then 0 up to infinity. The range, you can imagine, is from down to up. You're looking here again, minus infinity up to 0 in terms of the y values, and then you stop over here, then you jump across, and then 0 up to infinity, and that completes the evaluation of this hyperbolic cosecant. So remember just this specific fact: the hyperbolic cosecant, the hyperbolic cotangent will have a vertical asymptote x equals 0. The hyperbolic secant, the hyperbolic tangent won't have this vertical asymptote. They just will not, because you can't zero out that denominator. Anyhow, I think that brings us to the end of this. Remember these two, the most important, then hyperbolic tangent. Then after that, the remaining three are the least important. But in terms of any of you going into calculus or taking the advanced placement exam, knowing all of these 6 in terms of this basic information I've presented to you, the graph and this domain, range, and the definitions, That's about excellent information that you should keep in your mind. Thank you. Have a great day. Bye.